The birthday problem. This is a classic probability problem that asks about the probability that at least two people in a group of size n share the same birthday. We're going to assume that the other 365 days, we're ignoring leap year, are all equally likely to be the birthday of a randomly selected person. So any day in the year, you could be born. So first of all, A, how many people should there be in a class to guarantee? So we want to guarantee that at least two people share birthday. Well, let's see. If we know there are 365 days in a year, could there be 365 people who each have a different birthday? And the answer is yeah. But if we add just one more, there's going to have to be a duplicate. So let's start with a number of students. We're going to use n. There's 35 students typically in a Cal Poly class. So we're going to use n equals 35. And, I'm curious, make a guess at the probability that at least two people in a group of 35 share the same birthday. I would guess, I don't know, 5%. It doesn't seem like it would be that likely. Obviously, on an exam, by the way, I would not have you guessing. This is just to get us thinking about this. So it seems like there's 366 days, so it would be fairly unlikely to have that we would share a birthday. Two people would. How many different assignments of birthdays are possible for 360 or for 35 people? Is this the numerator or denominator of probability? Well, let's think about it. We want the number of possible assignments, so we want the number of arrangements. And hopefully you think, well, that's the denominator, that's the sample. Would we want to write this out? Probably not, because we've got 35 people and that could get ugly. Let's think about it. How could we come up with that number? We're actually going to use just that basic multiplication rule. The first person, so if we look at person one, how many days of the year can they choose to have their birthday? And hopefully you think, well, there's 365 days, so they can choose any day they want. Now, how many options does the second person have? Well, hopefully you think this next person could have any of the 365 days, and it's going to go all the way down to the 35th person. So all of them, 35th, 365 to the 35th. That's the possible number of arrangements. This is a huge number. In fact, if you put this into your calculator, most calculators, you are going to get an error. So this is the denominator, this is the sample space, and this is the size of it, and it is huge, okay? So this is the possible number of arrangements. Could all 35 people be born on the same day? Yeah. Would it be unusual? I would think so. Now let's describe the complement of the event we're interested in. All right, let's think about it. We want the probability that at least two share. We're going to use that complement, 1 minus the probability of what? Is it one shares? Well, no, that doesn't make sense, because if one person shares, they have to share with someone. The probability that at least two share is 1 minus the probability that no one shares. So that none share. Okay, so how many birthday assignments are possible so everyone has a different birthday? At first here, we want to know the different assignments of birthdays that are possible, and each person could choose any one of the 365 days. Now, we don't want a duplicate. So the first person would have 365 days they could choose from. What is the next person going to have? Hopefully you think, well, the first person's chosen their days, so there's only 364 left. And we're going to go all the way down to 331 for that 35th person. This number, if I calculate it out, is huge. It's a huge, huge number. 35 numbers multiplied together makes sense because there are 35 people. Now we want to calculate the probability that every person has a different birthday. Now remember, we've got the probability none share. What are those going to be? Well, the sample space is the value from C. And on top is going to be the value from E above. So it's going to be this number is going to go here. Now, you may think, well, what kind of number are we going to come up with? Well, it ends up being 0.186. Don't worry too much about the numbers here. I'm focusing on concepts. So now we want to use your previous answer to determine the probability that at least two people share the same birthday in a group of 35. Well, remember the probability that at least two share is 1 minus the probability that none share. And we end up with 0.814. That's really big. In fact, if I polled the class, I would that's over 80% chance that two people in this room will, if we were in person, would share birthdays. Funnily enough, my department is not huge. It has probably about 20 faculty. And myself and another faculty member, our wedding anniversaries are not only on the same day, but they're actually in the same year. So it's not as crazy as one would think. Now, H, given the expression for the probability of at least two sharing a birthday in a group of 70, we want to give that expression. And I'm going to say in 70 to be in a class of 70. So it's going to be 1 minus the probability that none share. What do you think is going to happen? Do you think the probability will go up or down? Well, I think about it this way. If there are more people, 70 instead of 35, is it more likely or less likely that two people would have the same birthday? And hopefully you think, well, it's more likely. This ends up being 0.999. I don't want to say guaranteed because nothing in life is guaranteed, but it's very likely. So it's the same number of days in a year, but there are more people, so more may share. So the probability more may share the same birthday, so the probability is larger. This is just showing you that these numbers can get really big in this birthday problem, that the probabilities may not always be necessarily intuitive to what we would think. And looking once again at that complement rule, something like this, though, remember, we would need coding to do.